so the question for this hour is as follows. We want to understand which numbers b are, well, case powers of something. So the question, the big question is, for what b does the congruence f to the power k is equal to b modulo the prime have a solution. This one solution. Yes, solution. Example. Oh, well, let me start with something you already know from real numbers. So this question is about what numbers b can you take such that you can extract the case root out of them. In real numbers, well, we know the answer completely. If you want, say, to extract a square root out of number, you know that you can do it for all positive numbers. And you cannot do it for all negative numbers. If you want to extract a cubic root, you know that you can do it for just any real number. And more generally, you can extract case root out of a number if, well, either case odd, then you can just extract the case root, or case even, and the number is positive, or non-negative. So in real numbers, this question is kind of stupid. I mean, not trivial, there is still something to think about, but still very simple. If you consider these congruencies, the answer turns out to be actually quite complicated. So we'll advance a little bit in the direction of understanding what is the answer. We'll get a definitive algorithm how to decide whether B has at least one case root. It won't be very fast, and well, when k is equal to 2, we'll get a better answer. So that's the plan. So let's start with some examples. Example. What can we say about this question when k is equal to p minus 1? So if k is equal to p minus 1. I want to solve such a congruence. X to p minus 1 is congruent to b modulo p. And the question is, for what numbers b does this congruence have at least one solution? Okay, 1. Oh, there. 0. Yes. So this congruence has a solution only if b is equal to 0 or 1. So let me explain. If b is equal to 0, of course 0 is a solution. Otherwise, well, take any non-zero number x, raise it to the power b minus 1. By Fermat-Little theorem, you get 1. So if b is equal to 1, we do have some solution. If b is not equal to 1, that's it. No solutions. Because x to the power b minus 1 is congruent to 0 or 1 for all modulo p for all x by Fermat-Little theorem. Okay, let me try a different one. So another example, p is 2k plus 1. And I want to understand, so I take an odd prime t, and I want to understand when x to the power k is congruent to b has a solution. Well, definitely b is equal to 0 works. But that's kind of a trivial case. It always works for any example of this kind, b equal to 0 works. B equal to 1 also works. Once again, in the trivial sense, it works always. Are there some other things which will work here?
Anything x squared. Anything. I mean, if you manipulate the exponent into p minus 1 divided 2, you know x squared is equal to 1.
Okay, yes. So this equation is indeed of the form x to the power of p minus 1 divided by 2 is congruent to b modulo p. If I know this, I know that, well, let me square both sides. I will get that x to the power of p minus 1 is congruent to b squared modulo p. But I don't know what is x to the power of p minus 1. By Fermat's theorem, it is either 0 or 1, always, for any x. So, conclusion, b squared, so by Fermat's theorem, b squared is 0 or 1 modulo p. And hence, b is equal to 0 plus or minus 1 modulo p. Okay, so the question now. I do know that 1 works. X to the power of k is equal to 1 has a solution, x equal to 1. What about minus 1? Does it work? So for b equal to minus 1. The question is now, does in fact x to the power p minus 1 divided by 2 congruent to minus 1 modulo p have a solution? Okay, starting with this equation, I assume that it has a solution. I concluded that b is 0, 1, minus 1. Well, but maybe I could think a little bit harder and conclude that actually b is just 0 or 1. Maybe for minus 1 there are never any solutions. Still, possibility. So what can I do? Can I actually solve this equation? I should find some number which raised to power p minus 1 divided by 2 gives me minus 1.
I don't think so. Yeah. Because you know x to the power of 1 half is equal to 1. If you square something, you get 1.
Yes, but that's okay. If I take this number, I square it,
Yeah.
I get minus 1 squared, which is 1. So it works. Is there such a thing? So
I think it's wrong.
yes.
If x is a primitive root, modulo p, then x to the p minus 1 over q shouldn't be 1.
Yes. Okay. Indeed. So, well, I wish somebody said that I could take minus 1, but well, it only works for some particular kinds of p. If p is what, 3 modulo 4, then minus 1 is a solution. But if p is not, well, if p minus 1 divided by 2 is even, then, well, I don't see any particular solution to this equation. I can't just take a number here, some particular number. But I can get the solution kind of more abstract way. I can take x to be a primitive root, modulo this number, this prime number p. So the answer is yes. X is a primitive root, or a primitive root. Modulo p. Any primitive root will work. Yes. So indeed, if you take such an x, then x to the power p minus 1 divided by 2 is not congruent to 1. Just because I know that the order of x is exactly p minus 1. So because since order x modulo p is p minus 1. It's not p minus p. This exponent is smaller than p minus 1. On the other hand, this number y, x to the power p minus 1 divided by 2, what could it be? But y squared, you know that it's x to the power p minus 1, which is 1 modulo p. So y is either 1 or minus 1. If y squared is equal to 1 modulo p, then y, this equation has at most two solutions, and the solutions are 1 and minus 1. Just see that. But we just ruled out one of them. One cannot be the answer. So the conclusion is, well, y is actually congruent to minus 1 modulo p. But that's exactly what we want. Y is x to the power p minus 1 divided by 2. So once again, for some particular kinds of p, we can perhaps see a solution. When p is something like 3 modulo 4, we can find an actual solution. Minus 1 is a solution. For other primes, well, it's not that easy to find a particular solution, but we do know that any primitive root will work. Okay, so maybe any questions about this example? Yeah?
It would also work if x has odd order, right?
If it has odd order, yes.
But would you be able to get those by the method we found before, where if you have a solution, you can find the others?
Yes. So if we take a primitive root and we multiply it by root of unity of this order, yes. Okay, other questions? Okay, now I think we are ready to attack the most general problem. Or maybe let's first assume that k is a divisor of p minus 1. It's kind of a little bit easier. So, next example. But this example is almost the most general one. If p is n times k plus 1. So k is the divisor of p minus 1. K is the divisor of p minus 1. And I want to understand, well, once again, I want to understand for which numbers p that is congruence have solutions. Well, once again, we can try doing the same trick. If I raise both sides to the power n, x to the power km, which is the same as b to the power m modulo p, x to the power km is just p minus 1. So this thing is, by Fermat-Rueppel theorem, either 0 or 1. So, if I have a solution here, I know that b to the power m will be equal either to 0 or 1. So, i.e., b is either 0 modulo p, or b to the power m is congruent to 1 modulo p. But once again, here is a necessary condition for this equation to have a solution. If I know that this equation has a solution, then b to the power m is 1 or it will happen that b is equal to 0. Is it also sufficient? Suppose I do have a b which does satisfy this equation. Do I get a solution? Well, the answer is yes. So let's see. So conversely, if you know that b to the power m is congruent to 1 modulo p. Because if b is equal to 0, there is nothing to think about. S equal to 0 is a solution. So I'm not even considering this case. This case is interesting. Suppose that b to the power m is equal to 1. Let me write b as a power of a primitive element. So write b as a to the power t for a primitive root So let me take my b and write it as some power of a primitive element. I want to show that b is actually a case power of something. So I want to show that this exponent t is actually divisible by k. Okay, let's see what this equation tells me. B to the power m, which is a to the power mt, is congruent to 1 modulo p. So no. And this holds. It's just that equation. But now it's written as an equation about the primitive root of a primitive root. What does it mean that a to some power is congruent to 1? It means that this power is divisible by the order of a, which is p minus 1. And p minus 1 divides m times t. But you know, m is already a divisor of p minus 1. So this means, or maybe let me write it like this: p minus 1 is m times k. M times k divides m times t. But that's the same as saying that t is divisible by k. So if I know that this condition is satisfied, then automatically when I write b as a power of primitive root, I get that this power is divisible by k. But that means, well, since t is s times k, for some s, and this means that b is a to the power of t, which is a to the power s to the power of k modulo p. And you see that, yes, you do get at least one solution. Here it is, a to the power s. X to the, so p x equal to a to the power s is the solution. So it's the same trick. basically the same trick as we've seen in the previous two cases. It's just slightly more generalized. So once again, the trick is like this. You take this equality, you raise it to the appropriate power to get the condition about b, that b raised to some power is actually equal to 1, modulo b. And vice versa. If you have this condition, then automatically you know that b is the power, is case power of something. And that follows, well, it's here we are once again using this non-constructive theory. There is some primitive root modulo p, and using this primitive root, I can rewrite this equality in much simpler form, in this form, basically. Let's do an example. So kind of sub-example. Suppose you want to solve such a problem. X squared is corresponding to -1 modulo p. You want to understand when can you extract the square root of -1. Well, without what we just did, it's not that obvious. I mean, you try different things. -1 squared is not -1, and p -1 squared, p -1 divided by 2 squared is also usually not -1. You try different stuff and you don't see an obvious solution. But we just have a complete answer. It has a solution if and only if -1 raised to the power p -1 divided by 2. Oh, let me assume p is what? P is even, p is equal to 2, well, that's the solution, x equal to 1. So let me consider the interesting case. So assume that p is odd, then p -1 is divisible by 2, and then we are in the situation that we just considered. When does the equation x to the power k is equal to something have a solution, and this k is a divisor of p -1? Well, here's a complete answer. Take this number b, raise it to the power, the smallest power to which you should raise to get p -1 here. So it is p -1 divided by 2. And you should get 1. And because of the considerations with the primitive root, we know that this works both ways. Not only this implication holds, which is almost obvious, but the opposite implication also works. And not in an obvious manner. I mean, you actually should consider something about, well, root of primitive root of unity. Sorry, primitive root modulo p. Okay, and finally, this just means that this number is even. So I can rewrite it further in a very simple way. -1 is, so p -1 is divisible by 4. So if p -1 is divisible by 4, then you can extract the square root of -1. If it isn't, you can't. Yeah.
How do you know the back condition holds both ways? Does it prove?
This one,
Yeah, you prove it holds from right to left.
yes. So once again, you go from here to here, you do the following. You raise both sides to the power p -1 divided by 2. On the left hand side you get 1, on the right hand side you get this number. Vice versa, it works this way. Take -1, write it as some power of a primitive element. I want to show that this power is even. Well, let me take this condition. -1 is some power of primitive element. this equality holds. So, well, if -1 is a primitive element to some power, here it goes. Then I know that 1, which is -1 to p -1 divided by 2, which is a to the power t times p -1 divided by 2, should be divisible by p minus, well, this equality should hold. It means that this exponent is divisible by p minus 1. It means that t is divisible by 2. So from this it follows that p minus 1 divides t times p minus 1 divided by 2. It means that t is divisible by 2. So once again, if it is some power of the primitive element, and you know that this equality holds, then this power must be even. That's our. But of course, we just made this argument in full generality. And well, if you understood this example in full generality, it just applies here. I mean, to be honest, it's quite a powerful result. I mean, if you think about it, you actually, well, it's actually hard to prove it. Here's an example of what you can do. If you recall, we once tried to show that there are infinitely many primes of some particular kind. For example, we showed that there are infinitely many primes of the form for k minus 1. And the trick was something like this. Take a number of the form 4n factorial minus 1. So I'm just trying to recall simplification. Let me formulate it this way. So it's just an observation, very simple observation. Every divisor of k squared plus 1, every prime divisor k squared plus 1 is 1 modulo 4. Every odd prime divisor. So that's the claim. I claim that if I take any number of this form and I take its prime divisor, it must be automatically 1 modulo 4. And just to explain that it's not entirely obvious, recall that any prime is either 1 modulo 4 or negative 1 modulo 4. Any odd prime is 1 modulo 4 or negative 1 modulo 4. And you could get a number which is, let's say the k is even, and this number is what? 1 modulo 4. But you could get a number which is 1 modulo 4 as a product of two numbers which are both negative 1 modulo 4. So it's not obvious that there is at least one prime divisor of this number which is 1 modulo 4. But in fact, every odd prime divisor of this number is 1 modulo 4. Here's the proof. If p divides k squared plus 1, then k squared plus 1 is congruent to 0 modulo p. then minus 1 is congruent to k squared modulo p. And now if I know that minus 1 is a square of something, if I know that this congruence has at least one solution, well, here's what I can conclude. 4 divides p minus 1. Okay, so it almost works like magic. I mean, we started with rather simple claim, which is not about, well, it is about congruence. It's about congruence modulo 4, but actually we had, on the way to proving this statement, we had to reduce the equation modulo p. We had to use a result about n minus 1 is a square, and then we got a result about, about what kind of a prime, some information about p modulo 4. So this proof is kind of short, but I would say it's remarkable. I mean, really, I mean, this my feeling is, well, it works because some wonder happens in between. And, well, the wonder happens somewhere here. Up to here, it is just simple algebraic manipulation, and this thing is actually a very hard step. And this step, we actually required, well, we actually used existence of primitive element modulo p. Well, a simple conclusion, there are infinitely many primes of the form for k plus 1. So maybe anyone sees how to construct, or how to prove such a result. Well, it's not conclusion, it's corollary. So the trick is like this. You should take a number which is of this form, which doesn't have small prime factors, and then, well, if for some reason it doesn't have small prime factors, it will mean that it will have large prime factors of the form for n plus 1. So how to produce a number of this form which doesn't have any small prime factors?
Again, n factorial.
Yes, exactly. So let me take proof n factorial plus 1, n factorial squared plus 1 is not divisible by any number between 2 and n. So it's relatively prime to all numbers. From 3 to n. It's because any such number divides this part, hence it does not divide the sum of this and 1. Hence, if p divides this number, and p is prime, then, well, first thing, p is greater than n. This number doesn't have any factor which is smaller than n. And second thing, p is congruent to 1 modulo 4. That's what we just proved. Any prime factor of such a number, k squared plus 1 is 1 modulo 4. So not only this number, produces one prime number which is equal to 1 modulo 4. You just take a factorization of this number to primes, all of its factors are equal to 1 modulo 4, and they are all quite large. And this kind of theory is really something which you couldn't do with bare hands.
This is probably non-constructive, right? We don't know how to find flash key, but we just know the existence.
Well, it kind of means it depends on what you mean by constructive. Constructive, well, it is constructive in the sense, here's an algorithm how to produce a number which is greater than 1 million and which is 1 modulo 4. Take 1 million factorial, square it, add 1, factor into prime numbers, take the smallest. You are right that it's not very constructive because it involves a step of taking 1 million factorial. It's a number with a huge number of digits, squaring it, adding 1 and factoring it, which is just impossible to achieve. So this kind of constructive, but not very constructive. Okay, so now once we see that it is useful to understand when you can extract case root of a given residue modular prime number, let's discuss the general problem. Let's prove the theorem, or rather record this theorem. We already almost have a complete proof of this theorem. X to the power k is congruent to v modulo p has a solution. If and only if b is equal to 0 modulo d, or b to the power p minus 1 divided by gcd of p minus 1 and k is congruent to 1 modulo p. Well, since it's a kind of experiment, well, in the second case, 1, 2, in case 2, there are k something minus 1 divided by GCD. Okay. And the solutions are there are GCD of k and k minus 1 solutions. I'm just repeating what we already know. But this result is new. Here we have a characterization of those residues which are k powers of something. And basically we don't really have anything left to prove. Well, maybe just a little bit. So let me mean, one option I can just repeat all the arguments that I had in previous case. In the case of k, we already know this theorem and k is a divisor of p minus 1. We just consider this as an example. I can repeat these arguments. I can take both sides of this equation, raise them to this power. On the left hand side, I will get a number which is divisible by p minus 1, the exponent which is divisible by p minus 1. So on the left hand side, I will get 1. On the right hand side, I will get this thing. So this thing is this equality follows from this equality and Fermat theorem, basically, and the converse direction follows in the same way. Just write e as some power of primitive element, and then you show that this power is divisible by k. Maybe it's a little bit better to formulate it to prove, oh, not really better. Oh, we should have some proof, and maybe this proof is easier to write down. So let me do it like this. I will write k as m times GCD of k and p minus 1 with m relatively prime. To p minus 1, I'll just factor my exponent k to one part which is a divisor of p minus 1, here it is, and another factor which has nothing to do with p minus 1, which is relatively prime to p minus 1. And then my equation is like this. It's x to the power m to the power GCD k and p minus 1 is congruent to b modulo p. And I know that this number is a divisor of p minus 1. So I can apply whatever I already know. So equation y to the power GCD k to p minus 1 congruent to b modulo p has a solution. If and only if one of these two equations hold, we already consider this as an example. So this is an equation that will form something raised to the power GCD of k to p minus 1 is equal to b. Let me call this something y. So now I have a new equation. Y to the power of this number is equal to b. I know that this number is a divisor of p minus 1. And for divisors of p minus 1, I already have my result. So since has a solution, if and only if b to the power of p minus 1 divided by this divisor, GCD of k minus 1 is b, is congruent to 0 or 1 modulo p. This follows from the example considered. Example that we already considered. And so if you have a solution, so if y is a solution of y to the power GCD k p minus 1 congruent to b modulo b, then how do we get back to x? I mean, I'm not interested in y, I'm interested in x. So to solve for x, so x to the power m is congruent to y modulo p. for x. And I know that this equation has only one solution, because m is relatively prime to b minus 1. It has one solution, it has a unique solution. Since GCD of m with b minus 1 is 1. So I kind of, after my original problem, computing, well, finding when the equation x to the power k is congruent to b has a solution, I factor it to two sub-problems. For one of the problems, the exponent is a divisor of b minus 1. For the other problem, it is relatively prime to b minus 1. I can solve each one of these sub-problems, and then the result is, well, I can combine them and get a solution to the full problem. Maybe some example. How many solutions? X to the power 15 is congruent to something modulo 15. 15 is too small. 31. 37. Let's try something here. Well, how to solve such a question? I have a question. It's really not about finding the solutions. The question is only about how many solutions are there. So the actual question is decide whether it has at least one solution, and then we'll apply the general results. So let's see. 37 minus 1, what is it? It's 36. The greatest common divisor of 36 and 15 is what? 3. So my equation is basically like this. It's x to the power 5th cubed is congruent to 3 modulo 37. If I manage to prove that 3 is a cube of some number, automatically I will be able to show that this equation has a solution. Because, well, I can convert 5 modulo 37, modulo 36, just quite easily. You can find 1 over 5. So this equation has a solution. It has a solution. So it has let me write down the full result. It has 3 solutions. Solutions. 3 to the power of what? 12 is congruent to 1 modulo 37. And it has 0 solutions. 3 to the power 12 is not congruent to 1 modulo 37. And that's not the final answer, because you should decide which one of the possibilities actually holds. And for this, well, we do have a method, successive squaring. To compute what is 3 to the power 12, we write it as 9 to the power 6, which is 81 to the power 3, which is something, and you can decide whether it is 1 or not 1. So for this kind of problem, well, 12 to 36 divided by 3. So it is, well, you know that if this number is a cube, then raised to the power 12, it will be something raised to the power 36, which is 1. So in one direction, all the implications are always easy to remember and write down. Just remember that we should raise both parts, both sides to the power, so that here you will get multiple of 46, 3 minus 1. The other implications will just should remember that they are parts of general theory. Okay, see you next time. And remember before the quiz next time.